So a couple announcements is that, first of all, today I won't be able to have office hours after the lecture. So I'm sorry about that. If you have any questions, I could probably make up office hours tomorrow or something like that if people have some kind of urgent question. So unfortunately, I won't be able to offer office hours today. Remember that the first exam is scheduled to take place a week from today, on the 27th, Wednesday, the 27th of May. So I had someone email me asking me a question whether that was the scheduled exam, and I believe it is, or I know it is. So I think that I've kind of settled on a way to give the exam. For those of you who are in either the Eastern time zone or adjacent to the Eastern time zone, what I'm going to ask is that you take the exam while on Zoom during the allotted class time hour, that is from 11:30 to 1. And the being on Zoom is so that I can, in essence, try to proctor the exam more or less. And then for those of you who are in very different time zones, I'm going to write a slightly different test with some small changes, maybe to some coefficients and things like that. And then I'm going to give you a time period during which to take the exam. And I'll ask that you record yourself taking the exam just so that there can be some amount of proctoring. Basically, the amount of cheating and honor court violations that UNC has had reported has like exploded since online teaching has started. So I'm going to really try to proctor the exam in some fashion, either by actually watching you take the exam on Zoom or by getting a video of you taking the exam. And that'll be on the 27th. Of course, I'll send out an email with more detail, but that's the current plan for the first midterm.
Is the exam going to be on Sakai?
Yeah, the exam will be made available on Sakai, so you'll open it up and yeah. So
do you have any idea what chapters are going to be on the exam, or is it just whatever we reach on?
It'll essentially be what we have covered, and probably I won't ask you too many questions on homework that you haven't turned in. So I would guess that the last material that'll be present on the exam is like whatever we cover maybe on the 25th of May.
Okay, that's Memorial Day, so the last class would be 22nd.
So the 22nd, yeah. Essentially, I guess probably you'll be tested on what we cover today, tomorrow, and on Friday. That's right.
Sounds good. Thank you.
Yep. So I'll send out an email with some more details and ask those of you who are in very different time zones to send me an email message so that I can get a sense for who will not be taking it during the allotted time. Are there any further questions on that?
Do you have any plan for partial credit?
I'm sorry?
Partial credit.
Partial, yes, certainly. So I don't really do, well, there might be some true false questions that I put on, but most of the questions will be asking you to, I don't know, like I can ask you problems like we've been working on in class. So I could ask you to sketch a slope field, in which case there would definitely be opportunities for partial credit because there are a lot of features in a slope field. I could be asking you to solve a particular differential equation, in which case there's plenty of opportunities for partial credit based on how far you get through the solution, or finding all solutions, things like that. So yeah, definitely opportunities for partial credit should abound.
So that makes it sound like we're gonna like scan in like a paper.
Yes, that's correct. Very good point. So for the testing, I will need everyone to get a Gradescope account that's associated with this class. I haven't set up a Gradescope account for this class yet, but I will have to do that today or tomorrow. And yeah, that'll be the system. Has everyone used Gradescope in previous math classes, or are there people who haven't had experience with it?
Yeah, I've used it.
Okay. Okay, so if you've used it before, it's probably, you know that it's not too difficult. All you really need to do is get an account, and then you'll be permitted to upload your documents basically at the end of the time period. So it's pretty reasonable, I think. Any other questions on the midterm?
Will you divide it up by like textbook section to say like what specifically will be on the midterm, or are we just going to look at the lectures?
I would say the best thing to do is look at what I've covered in the lectures, and then if I've spent some time on a topic in the textbook, I would urge you to look for problems that kind of pertain to, like, in the problems in the textbook that feel similar, and working out problems in the book that are close to sections that we covered should be a good way to practice for this test.
Thank
Any other question?
Would you say the homework is a good representation as well of things we might see on the exams, or is that not so much?
The homework is a good representation of the topics that I'd like to cover. One thing that is different is that the homework has all sorts of difficult computations on it. And since I'll be asking you to do the test with no calculator or outside aid, then all of the numerical aspects should be much simpler on whatever I ask you in the test. So I'm not going to be, I will try to avoid giving you horrendous expressions that you'd need a calculator to solve or to determine, basically.
Okay, thank you.
Any other questions? Okay.
When is the
yes.
test again? I kind of missed it. Sorry.
So there will be essentially two different ways that you can take the test. If you're in a time zone that is close to Eastern time zone, that is the time zone of UNC, then the test will be on May 27th during class time, so from 11:30 to 1. If you are in a time zone that is quite far away from Eastern time zone, then you'll have a window during which you can take a slightly different exam. It'll also be an hour and a half. And then everyone will upload their documents that they've produced from the test onto Gradescope, where I will grade them. I'll send out an email with all of this information probably tomorrow.
Thank you.
Oh, there are kind of a lot of notes today. So all of my notes for the previous lectures have been kind of a mess, and it's been difficult for me to find a good order for them. But I did post the notes from yesterday's lecture under resources, and I will probably essentially start doing that henceforth. So if you have any particular questions about lecture notes from previous lectures, I can try to find them, but it's been kind of difficult because I haven't been very organized with those. But going forward, every lecture should have a video on YouTube and a collection of lecture notes available in the resources tab on Sakai. Okay. Furthermore, I got a question via email, which was something as follows. I didn't respond via email, but I can respond here. Where is it? 1 second. So someone mentioned that they see a raw score on the homework assignments, but they noted that there's nothing for progress or the weighted score sections. My anticipation is that is totally normal. I think that the progress and weighted score probably depends on me doing something with your homework grades, and I haven't done anything. I've just assigned homework and left it at that. So I think that that's fine if you only see a if you only see a raw score. Okay, long list of kind of announcements and discussions about the structure of the class and midterm and homework and things like that. Any further questions?
Do you have anything to say about how long it is?
The midterm?
Yes.
I will give you the hour-and-a-half of class time to do it, but I won't write an exam that I expect to take an hour-and-a-half. So unfortunately, it's difficult to, it can be difficult for me to know how difficult my test is until y'all take it, but I don't try to write it so that it is supposed to take you the full amount of time. That's not my aim.
Okay, thank you.
Of course, I told that to my discrete class pretty much every time last semester, and there were timing issues for all of my exams. So we'll see how it actually ends up, but I'm not trying to make it last a long time. Okay, any other questions?
Yeah, are you gonna give us a little bit extra time at the end to upload onto Gradescope?
Yeah, there should be kind of a 10-minute time period where you should upload your exams, and 10 minutes should be enough time for you to tell me that, oh, I'm having some difficulty with this aspect. So I'll be online for that time period, and if anything's going wrong, you can either reach out to me in the Zoom or send me an email or something like that. So,
All
yeah.
right, thank you.
Any other questions?
On like previous tests, like we usually got 30 minutes to upload our stuff, and like I have a really bad camera on my phone, so like it's really hard for me to take pictures. Do you think like more like 20 minutes would be better?
I'm gonna stick with 10 minutes right now, but if things are taking a long time, just send me an email and I'll be understanding. But I'll just say 10 minutes at the moment, and then let me know how things are going. I'll just stay on the Zoom for like another 20 minutes or so after the time is done, so that I can work through any issues that people are having, you know.
Okay.
Is that reasonable?
Yeah.
Any last questions? Don't worry, I'm not impatient with y'all asking questions. But it sounds like we have exhausted the questions, so I'm going to start the lecture. So let me first go over what the content of our last lecture was. So last time, we were in section 2.4, and the main focus of 2.4 were two different existence and uniqueness theorems. Two different existence and uniqueness theorems. The first existence and uniqueness theorem was for first order linear differential equations. So can someone recall the conditions? So a first order linear differential equation looks like dy dt plus p of t y of t equals g of t. Can someone kind of remind me what the content of the theorem is?
dy dt and gt has to be continuous.
Yeah, so p of t and g of t, these two functions that we have.
I bet.
Yeah, I'm sure. So long as p of t and g of t are continuous, on on an interval around t0, then we get existence and uniqueness of a solution, y is equal to phi of t, satisfying, what are the two things that phi of t or y should satisfy?
The differential equation.
It should satisfy the differential equation, star maybe. And so existence is fine, but if we also want uniqueness, we have to ask for more than just something satisfying the differential equation. We have to ask that it satisfies
The IVP.
the IVP, namely plus the initial data, which we write as a y of t0 is equal to some y0, right? So this is essentially saying if you want uniqueness for your solution, you have to essentially demand that your solution passes through this fixed point, t0, y0. Otherwise, you're going to get a family of solutions. Okay. And the remark is that you can extend your solution to the largest interval where, or on which, P of t, G of t are continuous, are both continuous, containing t0. Okay. The second theorem that we discussed was for nonlinear first order nonlinear, which is dy over dt being equal to some function f of ty. So can someone remind me the conditions that we need to impose?
F of t and partial df dy have to be continuous.
Exactly. So we need f of ty and partial of f with respect to y. Well, here it should be with respect to, yeah, partial with respect to y of ty should be continuous where?
Rectangle.
Yes. On a rectangle, around, so a rectangle, say alpha less than t0 less than beta, and gamma less than y0 less than delta, around the point t0, y0.
Can you move the page up?
Oh, yep. Let me get myself set up properly so I can see what I'm doing.
Thank you.
And then, yes, thank you. Oh, 1 second. Okay. Right, so we need continuity of two different functions on a rectangle around t0, y0. Then what do we get? These conditions imply
It just exists.
Could you say that again? Sorry.
Sorry, wasn't it only existence?
Well, actually, you are able to get existence and uniqueness if you have all of this stuff. Yesterday, we did a lot of examples where we didn't have uniqueness, but those were in places where the two functions were not continuous on some rectangle around our initial point, right? Like in our example yesterday, we had places where the functions partial of y, or we had the functions f and partial of f with respect to y were both were discontinuous at y is equal to 1. And then we looked at two different initial value problems, one around -1, 0, and one around 1, 0. Oh, sorry. This is 0, -1, and this is 0, 1. And the point was, we do have existence and uniqueness over here. We weren't able to get uniqueness over here. But here, these conditions are saying that we're kind of in this case. There exists some rectangle around our initial data point such that both functions are continuous. And if both the functions are continuous, then we do get an existence and uniqueness theorem.
Did you say for the top example that we can get existence, we just can't get uniqueness?
In this case, so I'm not going to make any strong statement. There are deeper versions of this theorem, well, or more detailed versions. Basically, the idea is you should have existence as long as just f is continuous. In our case, for this example, f wasn't continuous, so we weren't technically solutions. We had solutions on an open interval whose boundary point was this data point. So it's like almost what we would call a solution. But the point is, the thing that we can remember perhaps is that when all of these conditions come together, we are guaranteed an existence and uniqueness theorem. And when any of these go wrong, we don't have a guarantee of the properties of existence or uniqueness. Perhaps that's the most simple way to think about it.
Right, thank you.
Yeah, sure. Okay, so as I've told you, we're going to get existence and uniqueness of a solution satisfying this differential equation and passing through this point. But there's a caveat. Is this function going to be defined on the interval alpha to beta? Do you understand my question?
Could you ask it again?
Yeah. So up here, for the linear first order ODE, the remark that I'm making here is that once we have any solution, we can extend that solution to the largest interval on which P of t and G of t are both continuous. And so you can kind of pretty clearly see just from the equation, just from the differential equation, what the maximal domain of your solution could be. And now I'm trying to ask a similar question here. If I can find a rectangle around my initial point, such that the rectangle is from alpha to beta in the t-axis and from gamma to delta in the y-axis, am I guaranteed to get a solution whose domain is the entire interval alpha to beta?
No.
No, right. All I'm guaranteed is the existence of an interval which looks like, say, t0 minus some epsilon, t0 plus some epsilon, where this entire interval is inside, it's a sub-interval of the interval alpha to beta, right? In pictures, if here is alpha to beta, all that I'm saying is there's some small interval around t0. Here's t0 minus epsilon, here's t0 plus epsilon. There exists some small interval around t0 such that y is equal to phi of t is a solution to the IVP. Here what I mean is it solves the differential equation and it passes through the initial data of t0, y0. and phi of t is defined on t0 minus epsilon t0 plus epsilon. Okay, so in some strong, important sense, all this is asserting is some local solution in some small local area around t0, and it's not immediate from the differential equation how far you can extend your solution, or on what domain your solution is actually a function. And we did some examples of this in the lecture last time, right? Where I did an example at the very end where both f and partial of f with respect to y were both continuous on the entire ty plane, but a solution to an initial value problem was still only possibly defined on some subinterval that was bounded either above or below. So just because your rectangle can be as big as you want doesn't mean that the solution can be as big as you want. So we just went over all of this, and so I'm kind of repeating myself, but repeating yourself is good in math because it takes like 7 times to learn anything. Are there any questions on this now that we're talking about it again?
So this might be a weird question, but when you say existence and uniqueness, if we don't have existence, does that mean that we just shouldn't be solving this solving the differential equation at all?
That's not quite true. What am I thinking here? I think that to get to a point where you don't have existence of solutions is a pretty tricky thing. But I can already imagine one thing, at least that comes from an example that you saw in calculus. Okay. So what am I trying to think about? Here's a function that you should remember from calculus, which looks like f of, let's say, t is equal to cosine of 1 over t, or sine of 1 over t. And this was a function that oscillates extremely rapidly as it gets close to 0, right? This is one of our classic pictures of some limit not existing because the function is wobbling too much around 0. So probably sine of t I should think about. It's like over here it's got big waves, but then as you get close to 0, it like smears itself against the axis. Then it's like not defined here, and then it goes like this. Something that I could imagine is that you could have a solution curve to the differential equation, which looks like this, but just vertically. Like you could have a differential equation which is telling you implicitly that something should look like this. And then it would definitely be impossible to have any solution exist around this bad point because the function is oscillating so much that extending the function any amount would always fail the vertical line test and would never be a function. There are probably much more simple examples of failure of existence to solutions to differential equations. Here's just one that I could imagine from calculus class. But basically, throughout this whole class, we're not going to be dealing with failure of existence of solutions to differential equations.
Oh, okay, this might just be me like having trouble understanding the relevance of this. So the point of this is not to figure out whether or not we should even be concerned with solving. Am I correct?
The point of this is to show you how bad things could possibly be, in the sense that even some very simple nonlinear first order differential equations fail to have existence and uniqueness guaranteed everywhere. And it's just a fact of life that you have to deal with when you're thinking about differential equations, is you can't always assume uniqueness of solutions, and you can't even necessarily always assume existence of solutions. And so that's kind of like a first thing that you should remember about differential equations. And then you should examine, well, if you're trying to think about a particular differential equation, you should say, where am I guaranteed some amount of existence and uniqueness? And the answers are provided by these theorems, which say, as long as you avoid some certain bad areas, then you are at least locally guaranteed existence and uniqueness for your differential equation.
Okay, that makes sense.
So this is saying that in most places, as long as you avoid these bad subspaces of the XY plane, say, then you are guaranteed at least some small amount of existence and uniqueness of a solution.
Okay, thanks.
It's a good question. Any other question on this?
I had a question about the example that we did yesterday.
Yeah,
So
sure.
when we did the 3x squared plus 4x plus 2 over 2y minus 1, like that was equal to dy dx, we were talking about how we were not guaranteed a unique solution for y of 0 equals 1.
Yes.
But y of 0 equals -1 like should work.
Yes.
So I was just trying to solve it, and I think because of like how we have squared, will we get a unique solution for y of 0 equals -1?
Yes, we will actually. And the point can be seen by going back to the actual slope field diagram for this picture. And just as a kind of a sketch, the slope field diagram looks something like this, or the integral curves to the slope field diagram look something like this. So the idea of whether a solution exists locally is essentially, can I locally write down a function, or let me say it this way. Think of these as curves in space, parametrized by some time variable t, right? This is some parametric curve in space. We could write down equations for it. The question is, locally around a point, can you find a honest function which describes that parametric curve as well? And the point is, anytime that you're around y is equal to 1, you cannot find an honest function which represents this curve locally, because every such curve fails the vertical line test. So if you want to write an honest function, you either have to restrict yourself to just the top part, which is one branch of the square root. So this is a function on this interval. Or you have to restrict yourself to the bottom part, which this is the bottom branch of the square root, and this is a function on this interval. But the real thing that I'm pointing out here is the thing that goes wrong is the vertical line test is failed when you're around here, when you're around y is equal to 1. When you're at x is 0, y is -1, then the only curve, or the curve that passes through this initial data right here, can actually be described by a function because it passes the vertical line test everywhere. And indeed, the positive branch associated to this solution is all the way up here and doesn't solve the initial value problem because it doesn't pass through the point that we're interested in. So the bad behavior somehow crucially has to deal with this y is equal to 1 line, where the curves can't possibly describe functions, or can't possibly be described by functions, because they fail the vertical line test here. But here we can find some local neighborhood where this curve doesn't fail the vertical line test, so we can actually describe it by a function.
That makes so much sense. Thank you.
Yeah, of course. It's yep.
If you do create like when you say like create like a local function, you're not restricting the domain here. Are you restricting?
I absolutely am. I absolutely am restricting the domain of the function that I write for solving this IVP to some small interval around here.
Yeah,
And I
okay.
know, well, go on.
But you're also restricting the range mostly, right? Because like if you just restrict the domain, then it still fails the vertical line test.
If I just restrict the domain?
Yeah.
No, if I just in this picture, if I only restrict my domain to here, sorry, this picture is getting kind of messy, but if I restrict my domain to here, and then I write down a function describing this curve on this domain, it satisfies the vertical line test, right?
Satisfies it, but what about the portion of it like up top?
You mean if I tried to extend up to here?
Well, I'm just saying, like, if you plug in, like, it looks like, you know, t of 0 for that part of the curve, right? Like f of 0, sorry, where t equals 0, then
here?
Yeah. If you go straight up, wouldn't you intersect the
here?
Yeah.
So let's kind of remember something about let's go to a more simple example. So a more simple example here is just a circle, right? So a circle of radius 1 can be written as the set of points satisfying x squared plus y squared is equal to 1, right?
Yeah.
And its graph looks like this. And something that you all know very well is that this can't possibly be described by a function f of x, y is equal to f of x, because it doesn't pass the vertical line test. However, if we restrict ourselves to some local chunk, say that we restrict ourselves here on some interval, then there are two different functions satisfying this equation. They don't intersect at all. One is given by y is equal to the positive square root of 1 minus x squared. That's this chunk. And that's an honest function. And then there's a second honest function, y is equal to negative square root of 1 minus x squared. And this is the function which exactly describes this curve down here. So essentially, what I am demanding of this differential equation is I'm asking for, one, a function, y is equal to f of x, which satisfies x squared plus y squared is equal to 1, and 2, passes through 0, comma, negative 1. And now you see that once I specify some additional data, this function does not work, and this actual function does. And this function on this limited domain does indeed pass the vertical line test, because it's just this.
Okay, that makes a lot of sense. Thank you.
Yeah, yeah. These are great questions. I'm really happy to be discussing this this material, because these questions of existence and uniqueness lead to some very important questions about what does it mean to be a solution? What does it mean to be a function? What are we asking our functions or solutions to satisfy? And you can see that this example actually didn't explicitly involve any differential equations at all. It's just asking for a function which satisfies this and which passes through a point. But we can see kind of similar behavior. And of course, what you can see here is the exact same story. It is not possible to have a function such that x squared plus f of x squared is equal to 1, so satisfying this, and f of 0 is equal to negative 1, defined on the interval, let's say negative 1 to 1, right? There is no possible, well, on any interval, say -1 minus some little epsilon and 1 plus some epsilon, right? I can't possibly define a function on some big interval which satisfies both things, because satisfying this equation would force it to fail the vertical line test at some point. So here, once again, we see the only chance for for having a function which satisfies both of these properties is for it to be defined on some small interval around the initial data of 0, -1. Is this helpful?
Yeah, that makes sense.
Right, so this is kind of what we're running into when we say we can't extend the solution beyond some small interval around the initial data. I cannot extend this function, which is very nice here. There's no way to extend this function such that it both solves the differential equation and passes through this point all the way to somewhere over here. It can't be done. Oh, I'm sorry, you can't see that. Okay, so let me give you another exercise that deals with this sort of material. Exercise, check the following. Check that y1 of t is equal to 1 minus t, and y2 of t is equal to t squared, or sorry, negative t squared over 4, are both solutions to y prime is equal to negative t plus square root of t squared plus 4y, all divided by 2, with initial condition IVP y of 2 is equal to -1. So I'll let you work on this for a couple minutes.
Sorry, that's negative t squared over 4, right? For y2?
Yeah, negative t squared over 4.
Okay, thank you.
So this exercise doesn't really have too much mathematical content in the sense of what you're being asked to do, because you're really just being asked to check that two different things are solutions, which is not so difficult, but it's the outcome that is interesting. So have people checked that y1 is a solution?
Yeah.
Not quite.
Okay, no problem. Take your time. Will I be posting? Will I be posting the actual recordings of the lectures in addition to the lecture notes? Yeah, Carolyn, they're actually already available on YouTube. I sent a link, I believe. I could send another one if you'd like. But thus far, all of the lectures are available except for the first one online. How are we doing in terms of the checking that these things are solutions?
I think we're good.
Think we're good? Okay. I just want to go through, well, I'll go through it pretty quickly. So remember what it means to be a solution. All it means is that you plug in y to both sides and you get the same thing. So checking that this function is a solution to this differential equation means that on the left side, I take the derivative with respect to t, and I get -1. So 1 d over dt of 1 minus t is just equal to -1. That's the left-hand side. On the right-hand side, I have negative t plus the square root of t squared plus 4 times 1 minus t, right? Y is equal to 1 minus t all over 2. T squared plus 4 times 1 minus t will factor. So this side is going to be equal to negative t plus the square root of t. Let's see, it's going to be what? Minus 2 squared over 2. So then we're going to get, this is equal to negative t plus t minus 2 over 2. And you'll see that you'll get, this is equal to -1. So this is the check that's required. This is equal to this. This is the check required to see that y1 is a solution. Y2 being a solution is easier to see. Okay, so what do we have here? Well, we have a differential equation with two different solutions satisfying the IVP. Both of these are solutions to the differential equation, and when I plug in 2 for t, I get -1 both times. So automatically I know that this is a that the solution is not unique, right? So note, solution to the IVP is not unique. And indeed, we can expect that because if we take the derivative of this function with respect to y, we're going to get things involving square roots of, or like 1 over square root of t squared plus 4y and things like that. And there's going to be a place, namely 2, -1, where the partial derivative of this function with respect to y is not continuous. And so we shouldn't expect the solution to be unique. So shouldn't expect uniqueness due to partial of f, partial of y not being continuous at 2, -1. And then there's one more feature that I want to point out here that we didn't discuss yesterday, is that there's actually a family, exists a family of solutions to this differential equation.
Can you move up, please?
Oh, sorry, is there a question? Oh, I need to move up. There exists a family of solutions to this diff EQ, which looks like y of t is equal to ct plus c squared. And one can check that this family of solutions indeed satisfies this differential equation. That's not too difficult. The important point that I want to remark is that you showed that negative t squared divided by 4 was a solution. Could negative t squared over 4 ever be of this form?
No.
No, this function, no matter what c is always linear in t. That is, the highest power of t is 1. Whereas here, this is a solution where the highest power of t is 2. This is quadratic in t. So some additional bad behavior of nonlinear differential equations is that there may be exceptional solutions which are not found as members of a family. So this behavior is not found in the linear differential equations, where essentially we can show that every solution is one of a family that we see. But here, in the nonlinear case, we see that we've got a whole family of solutions that look like this. And indeed, 1 minus t is part of this family, right? If I take c to be -1, sorry, it's hard to see both of these at the same time. But if I take c to be -1, then I get this member of the family. But this is a solution which never appears as a member of this family. So in general, it is somehow less correct to talk about a general solution of a nonlinear differential equation or a nonlinear IVP, because there might be solutions that don't fit inside of a family of solutions. Is it kind of clear what I'm trying to discuss here?
Yeah.
Yeah, so this is just kind of another aspect of how linear differential equations have all sorts of favorable properties in terms of their solutions. And the moment that you even get to a little bit of a nonlinear differential equation, and some nonlinear differential equations we can actually tell a lot about, right? Like the separable nonlinear differential equations, we essentially know all that can be, or all that needs to be known about the solutions. It's just that the set of solutions doesn't have so many nice properties. First of all, there could be members outside of the families. Second of all, the solutions don't have to be unique. Third of all, maybe they don't even exist, et cetera, et cetera, et cetera. And by exist, I mean exist as functions. So, okay. Now I would like to kind of move on from the material from 2.4. Before I move on, are there any questions? Okay, this took up quite a bit more time than I anticipated, but that's fine because we were discussing some very fun and interesting aspects about what it means for solutions to exist and things like that. So I'm not happy or unhappy at all. I think that was a good use of our time. And questions are just good in general, so I'm happy. Okay, let's move into 2.5. Essentially what I'll be doing here is I'll be introducing another class of differential equations that are pretty easy to solve, and another collection of models that the solutions to these differential equations are supposed to represent. So another class of diffie-qs we can actually solve. I probably shouldn't write that headline too many times because it'll feel like the whole class is this headline. But okay, so these are called autonomous differential equations. First order. So I'll kind of contrast this with the separable case. So in the separable first order, the general picture is dy over dx is equal to f of xy. And then separable means what?
M of y dy is equal to n of x dx.
Yeah, can be written as m of x plus n of y dy over dx is equal to 0. This is what it means for a first order nonlinear differential equation to be separable. What it means to be autonomous is something different. So autonomous are those differential equations of this form: dy over dx is equal to f of x y, but actually I just want this to be equal to f of y. So in other words, f is just a function of y, not x. So there are plenty of examples, and essentially the ones that we're going to be discussing today are: what if dy over dx is equal to either a polynomial of y, where p of y has degree 1 or 2. So this is what we're discussing today, but an autonomous differential equation just means that you have dy over dx is a function of y, without any x's explicitly involved. Although remember that x or y depends on x. Y is a function of x. So let's do our first example, first basic example. The first basic example is probably dy over dt. I can switch back and forth between x's and t's, hopefully without confusion. If this is a constant. If dy over dt is a constant, then this is a calculus problem. And indeed, if this function is just a function of t, then that's once again a calculus problem. Dy over dt is equal to f of t, calculus problem. But now what we're going to be doing is, so if this was the first basic example, the second basic example is dy over dt is equal to r of y. And this is not a calculus problem. This is a problem in differential equations. Okay, but we already know how to solve these because this is actually a first order linear. And so here, how do we solve first order linears?
Using an integrating factor.
Yes, solve via integrating factors. And I'll just write out what a general solution to this thing looks like. General solution looks like y is equal to y0 e to the rt.
Can I also treat this as a separable equation and divide it by y, so I get 1 over y dy and r dt?
Yes, you can do that as well, and you'll end up with the exact same solution.
Okay, cool.
Yep, you'll get the same thing, because once you do that, you'll have something involving d over dt of natural log. So yeah, if you divide by y, then this thing looks like the derivative of natural log of y being equal to r.
Okay,
integrate both sides by t, exponentiate, and you'll get solutions that look just like this. So yes, good point.
Nice.
Okay, and the picture of these solutions is essentially that of exponential growth, where these are different y zeros, initial conditions. Okay. Okay, so these two examples we already understand very well. This because you took calculus, and this because we did it last week. So the next example up is what's called a logistic growth model. And the idea is we want dy over dt to be equal to h of y times y, where h of y is linear. And we're going to choose h so that it satisfies the following three conditions. We want h of y to be close to r for y small. We want h of y to be less than r for y large. And we want h of y to be less than 0 for y too big. So the idea is, once again, this differential equation is a differential equation that could be written down by someone who's trying to model something. So up here, if we think about this as a population model, then R is the rate of growth of the population. So for instance, if you plug in a rate here, like 2 or 4 or whatever, I mean, any number, then essentially the curves that you'll get here are the growth, the unrestricted growth of that population. So for instance, if you, once again, take the nice example of rabbits, and you assume that they reproduce, I have no idea, I've never had rabbits. I don't know how often they reproduce. But if you just say that rabbits reproduce so that, you know, the population doubles every 2 years, then you write down what would solve that differential equation of population doubling every 2 years, and you get some exponential curve. Okay. But obviously not all, or populations don't usually grow exponentially. So the idea is we should change the rate of growth so that it depends on the current population. So finding a y that satisfies these things seems like a more reasonable way to model growth of a population. When the number of the population is small, it should be close to some standardized growth rate r. When the population is getting bigger, the rate of reproduction of the population should be decreasing. And there should be some threshold beyond which the population is too big. Say the environment can only sustain 10 trillion rabbits. And if you have quadrillion rabbits, then there's not enough food. And so then the population should be declining. So all that I'm saying is one important way to think about differential equations is remember that in a lot of situations, the first thing that you should write down is the differential equation, and then you should solve it. So it's reasonable to come up with a model that satisfies these properties and say, this is a naive model for population growth, for instance. Any questions with what I've been discussing here? I don't know if that was clear or confusing.
That was making sense.
Okay, great, thank you. I really appreciate that. Okay, so it turns out that there's an easy function which does this. And it's linear, and it's h of y is equal to r minus ay. So let's examine that this function h has the properties that we're asking. Well, when y is very small, then h of y is indeed near r. As y gets larger and larger, there's going to be some point where we hit 0, right? Let's assume that a is greater than 0. A greater than 0, r greater than 0. There's going to be some point at which y is big enough such that this is 0. And then when y gets much bigger, then h of y will be negative because I'll be doing r minus some really big number. So that's the point where the population is so big that the population should be decreasing. Wow, someone is waiting to come to class. I don't know how long this has been the case. Okay, so this is a function which satisfies these conditions over here. And so what I want to do is actually rewrite this a little bit. And so we can discuss an actual model that was introduced, I think, in the 1800s. So we're interested now in the differential equation dy dt is equal to r minus a of y. So this is kind of our h of y times y. And just for ease, I'm going to write this as r of 1 minus a over r times y. And then I'll make the substitution k is equal to r over a, and write this at the end as r 1 minus y over k times y. And it may seem that I've just done a kind of meaningless change of variables, which is true, but this form is kind of nice for a couple important reasons. Okay, so hopefully what I've done here is I have motivated to you why one might wish to study a differential equation of this form. And the essential idea is that solutions to this differential equation should be slightly more sophisticated models of population growth than just the flat exponential model, where you say all populations explode always. So that's kind of a motivated reason why one would write down this differential equation. So the first thing that we should do is learn as much as we can without solving. Okay, so given the differential equation, dy over dt is equal to r times 1 minus y over k, y. what are some things that we should look for before solving this differential equation?
K and R.
Sorry, could you say that again?
Just like the values for K and R.
So we're kind of assuming that the values for K and R are specified. So assume that R greater than 0 and K greater than 0 are given. So essentially I'm asking, what tools do we use to think about differential equations that don't involve solving the differential equation?
Slope fields?
Yeah, let's look at, there are a couple things that we can try to read off quickly. We can try to read off slope fields. We can try to read off equilibrium solutions. Right? Now, let's do the equilibrium solutions first. If dy over dt is this function, what does it mean to be an equilibrium solution?
Let dy dt equals 0.
We want dy over dt to be equal to 0, exactly. So the equilibrium solution should appear when this function is 0. When is r times 1 minus y over k times y 0?
When r equals to 0 or y equals to k and y equals to 0?
Yes, so we're going to assume that r is some fixed constant greater than 0.
Right.
But the point is, we get such solutions when y is equal to 0 or y is equal to k.
Okay.
Right? So the very first thing that I can do when I start writing my slope diagram is I know that the slope at 0 is, sorry, this is like, I wish I had different colors, but the slope field here is 0. And indeed, I know that's going to correspond to an equilibrium solution, which is just flat at 0. And I also know at y is equal to k, I'm going to have slope field, which is just totally horizontal. And I also know that I'm going to have some solution, right? Y is equal to k is a solution to this differential equation, and it doesn't change in time. Right? So I'm going to have these two solutions. The next question is, if we want a slope field, the important thing we want to know is whether the slope is positive or negative in these different regions. So when y is greater than 0 but less than k, is dy dt positive or negative?
Positive.
Yeah, positive slope here. Right? Because y is positive, and if y is less than k, then 1 minus something less than 1 will be positive, and r is positive. So I have positive slope here. And then what about above the line y is equal to k? So now I'm assuming y is equal to like k plus 1 or something. Is the derivative positive or negative?
Negative.
Negative. So I have negative slope up here. Okay. And we can actually go even further. We can start thinking about, and by the way, you can kind of understand this in the same way that you thought about in calculus by actually graphing this function, r1 minus y over k times y. The graph of this function is going to be a parabola with a 0 here and a 0 at k. Right? And it's going to be positive in some areas. And did I do this correctly? I feel now that it should be something that looks like this.
Can you move up, please?
Because in between here, it's positive. Yeah, this function is positive in between 0 and k. So it should look like this. And so you can kind of read off what the whether the slope is going to be positive or negative by looking at the graph of f of y versus y. Okay, and something that we can do more is we can actually look at inflection points. Of solutions. Now, remind me from calculus, what is an inflection point? Or what, it's really about concavity. How do we think about concavity of functions?
Doesn't the concavity of a function change at the inflection point?
It does indeed, yes. That's correct. And what tool do we use to try to investigate concavity?
It's the first and second derivatives, right?
Yeah, in particular, it's the second derivative. So concavity is governed by the second derivative. D squared y dt squared, right? So dy squared, or d squared y over dt is equal to d over dt of dy over dt, which is equal to d over dt. What is dy over dt equal to? From our differential equation?
R1 minus y over k times y.
Exactly. This is some function f of y. I mean, you told me exactly what the function was. It's up here. dy over dt is equal to r times 1 minus y over k times y. This is just some function of y. So the second derivative can be found by taking the derivative of this function of y, which is going to be equal to, by the chain rule, what? How do I take the derivative of a composition of functions?
Is it f function y times dt plus derivative of y times t?
I don't think I should have pluses. I think this is a chain rule where f is a function of y and y is a function of t. So the chain rule says I should take the derivative of f with respect to y times the derivative of y with respect to t. Do you agree with this?
Yes.
So the point is, to examine the concavity of solutions, we should examine d squared y over dt squared, which in our case is equal to f prime of y times dy over dt. In our example, dy over dt is equal to r 1 minus y over k times y. And this is our f of y. What's the derivative of this function with respect to y? Well, it'll be r times 1 minus 2y over k. Do you agree? You could do a product rule, but what would be easier is to multiply the y through. So I get r times y minus y squared over k. And then I take the derivative and I'll get this.
Okay. Yeah.
Yeah.
Times dy over dt, which is just this function again. R times 1 minus y over k times y. This is d squared y over dt squared. Is this okay? It's maybe a little confusing what happened here, but what I'm investigating is the concavity of the solutions. And the point is, if you want to think about concavity, you should think about the zeros of the second derivative. Where is this function 0?
When y is 0, y is k, and y is 1/2 k.
Exactly.
2k. Yeah.
Okay, so on my slope field, if I'm trying to write a nice slope field, I break things up into several places. First of all, there's this equilibrium solution at y is equal to 0. I'll make a dotted line at y is equal to k over 2. And then I'll make another line at y is equal to k. We know that the solutions are increasing here, and they're decreasing here. And then if you start checking the concavity, it turns out that concavity up, so concave up here, it'll be concave down here, and then concave up here. This is just something that you can check by examining this function and asking whether this function is positive or negative in the intervals determined by when this is 0. So find out when this is 0. It's 0 at these points. You check the intervals in between to see whether this function is positive or negative, and you can check concavity. All of this can give us some very precise data about the slope field. Things are positive and concave up over here. So a solution would look something like this. Increasing, concave up. Here, it's still going to be increasing, but it's going to be concave down. So we're going to get something like this. And similarly, if we start up here, then it's just going to be concave down. So it's going to look something like this. Here, they're all going to be concave down. And then if they start down here, they're going to start concave up, then concave down. And then everything above is concave up, but decreasing. So things look like this. Okay. Is it understandable how I came across these kind of guesses for the solutions of the slope field?
Yes.
Great. It's incredible how I didn't cover that much material today. Well, we did. We covered a lot. But... Okay, so this is a general picture of what the solutions to this differential equation should look like. Very good. Let me give some important notes. So note, the change of variables, when I introduced k for being equal to like r over a or something, it seems kind of arbitrary when I first made that change of variables, but we see here that k has significance in this model. So for instance, if you were trying to model a population with this, then k would be called the carrying capacity of this population in this environment. Because when the population starts above the carrying capacity, the population decreases and gets very close to the carrying capacity. If the population starts off at exactly the carrying capacity, then the population never changes. We have an equilibrium solution. And if we start off below the carrying capacity, then at first the growth looks exponential, but then at a certain point, as we approach the carrying capacity, the growth of the population tapers off and approaches the actual carrying capacity in the long term. So in this model, all of the populations that don't start off at 0 approach the carrying capacity. So in this model, let me give a definition. Equilibrium solutions like K here are called stable. Let me give a precise definition really quick. Are called stable if for y0 greater than k and for y0 less than k, we have the limit of our solution as t goes to infinity of y of t being equal to k. So the point is, if I take some basket of initial data around k, all of those solutions have a limit of k as t goes to infinity. So here probably I should really define some interval to define a stable solution. And then 0 here is an unstable equilibrium solution. And the idea here is that the only way for the limit as t goes to infinity of y of t to be equal to 0 is if y0 is equal to 0 on the nose. That means if you pick any solution whose y0 is not 0, then its long-term behavior doesn't bring it close to 0. Its long-term behavior brings it close to k. The only way to have a limit of the solution as t goes to infinity being 0 is if the initial population is exactly 0. Is this idea of a stable equilibrium solution and a unstable equilibrium solution kind of clear just from the picture at least?
Yeah.
Great, thank you.
Can you move the page up a little bit?
Oh, yep, of course.
Thank you.
So this definition of stable that I've given here is not a very strong or workable definition of stable in the long run. There are lots of solutions that you want to call stable or unstable based on sort of different criteria. But all that I'm trying to give here is not like an official definition, but an idea of what it means to be stable versus semi-stable. And essentially, a stable one means that there's some collection of solutions that tends towards that equilibrium solution as t goes to infinity. An unstable solution is one where the only way that you can have limiting behavior close to that equilibrium solution is if you start at that equilibrium solution. As a last comment, since it's 1 o'clock, the physical idea, one very physical example of this is that if you consider a pendulum, there are 2 stable solutions for a simple pendulum. One stable solution is when theta is equal to 0. Basically, the pendulum is not swinging at all. And then an unstable solution is when the pendulum hangs straight up. In some sort of ideal world, it's possible that if there were no friction or no energy whatsoever, that you could put a pendulum straight up and it would stay here. But if you move the pendulum even a tiny bit, then the solution will start swinging, and over time, it'll eventually approach this solution. So in physics, this is maybe the first example of a stable solution to a differential equation, namely motion of a pendulum, and an unstable solution to the equation of motion of a pendulum. Okay, it's 1 o'clock. I've already held you a little late, so have a lovely afternoon.
Thank you.
Thank you.
Thank you. Thank you.
Sorry about the no office hours today, but I can do them Thursday if people have questions, and of course I'll do them Friday.